Chapter 2, Section 4, Question 1, Type 1 of 2. Distance equals rate times time. You're going to have a lot of distance equals rate times time problems. You're going to have it in Chapter 2, Chapter 4, Chapter 6, Chapter 8. You're not going to get rid of them after that. They're going to come back in your college classes as well. So here, in order to organize our information, we're going to make a distance equals rate times time chart. And that tells us how they're all related to each other. We have a train traveling at 130 miles per hour. Miles per hour, the per makes it a rate. It's comparing the miles to the hours. So the train has a rate of 130 miles per hour. And a bus, notice that I'm putting a T and a B so I know which one is the train and which is the bus, travels at 80 miles per hour. They start at the same spot and then travel away from each other. Notice that I'm doing that with my hands, but let's draw a picture. Here's the spot that they're starting. The train goes one way, and the bus goes the other way. How many hours will they be 357 miles apart? I don't know how much time that is, but I'll call this X. Some people want to use T for time. So the time for the train and the time for the bus is the same amount of time because they started at the same spot and they traveled away from each other. Rate times time equals distance. 130 times x equals 130x. 80 times x gives you 80x. And that says that this is 80x and this is 130x. And from geometry and real life, the two little pieces add up to equal the big piece. That's how we make our equation. The two little pieces add up to equal the big piece. Adding those together, gives me 1.7. You could do that by hand. There's only one variable, so we have variables, equation, showing work to solve. And then over here we have 1.7, and it's miles per hour, so the time is given in hours. Chapter 2, Section 4, Question 1, Type 2 of 2. Again, distance equals rate times time, but this time they're going in the same direction. Last time they were going in opposite directions, and this time they're going in the same direction. So we're still going to use our distance equals rate times time chart. Very useful, and eventually the idea is that you will understand these problems enough that you may not need it, but for right now, we want to have this. Our train is going 130 miles an hour. I feel like that's the same rate it was going last time. The bus is still going at 80 miles an hour. That is still the rate it was going last time. They start at the same spot and they go in the same direction. Now, I don't really want to have two arrows right on top of each other, so I'm going to write it just a little bit above the other one. In how many hours will they be 260 miles apart? Since the train is going faster, there's going to be a small amount of distance in between there, so we have 260. We can still use x for our time, and we have 130x and 80x, 130x and 80x. There's a couple of ways that you can set these up. Last time we added up the distances to equal the total. Here you could subtract them to equal the total. 130x minus the 80x gives us the little distance in between, which is 260. However, some people using this picture also use the two little pieces add up to equal the big piece, and they get 80x plus 260 equals 130x. Either of those is a fine way of solving them. I'm going to use this way. We subtract that and we get 50x equals 260. Dividing on both sides, showing this wonderful work, and we get x is equal to 5.2. and this is still in hours. Now, something to think about as you're doing this, some students have gotten an answer of 52 because they made a mistake with dividing. I would like you to know that my people, when they are riding a bike, driving a bus, something like that, these numbers for how long they're doing this should probably be 8 hours or less, because if you have someone driving a bus for 52 hours, at some point they're going to pass out and possibly die. That's not cool. So make sure that you look and make sure that these are reasonable. They should also be positive. Chapter 2, Section 4, Question 2. This is a distance equals rate times time problem, but it has different start times. So we are still going to start off with our handy dandy distance equals rate times time chart. And we're going to have a runner, and the runner is running at 11 miles an hour. The per is a rate, and then we have a jogger that's jogging at 9 miles per hour. They start at the same spot and they travel in the same direction. Hey, I feel like this is just like the last problem. And it says the jogger starts 1 hour before the runner. So we have to look at this and use logic. If the jogger starts an hour before the runner, the jogger started before the runner. If the jogger started before the runner, who has the 1 hour of extra time there? So the jogger started before the runner. The jogger has more time. So we have 11x and we have 9 times x plus 1. And the question doesn't say how far apart are they. It says in how many hours will they meet up with each other. So if you think about that, their distances will be equal. Now think about this. We have some hand signs for you. We have them going in opposite directions, in which case we will add them together. We have them going in the same directions, in which case we can subtract them to find out the little bit of time or distance in between, or we can have them going in the same direction until they're equal to each other and your hands can make little equal signs. So here we have the time for the runner and the time for the jogger. And we want these to be equal to each other. So if you look at my picture, it makes a nice little equal sign where 11x is the runner and 9 times x plus 1 is the jogger. Here's our equation. We want this to equal that. That's how they're going to catch up to each other. Distributive property from chapter 1. Getting everything all on one side. For your x's, isolating your x's. But wait, I have an x and an x plus 1. If I have an x and an x plus 1, just like in chapter 2, section 3, I need to find x plus 1. There is our handy dandy answer block. Very important. Finding all those answers and then putting them here with their labels. Be careful on these. One of the problems is that instead of starting an hour before, they'll start half an hour before, in which case it would be x plus a half. You may use x plus 0.5, but I've had some students when it says maybe they start 30 minutes before, they'll put x plus 30, or a half hour is they'll use x plus 30. That means that they started 30 hours before, over a day ahead of the other person, in which case, again, those people are going to die from jogging for 30 hours. So don't let them do that. If this is in hours, then this should be in hours as well. So make sure that those units match. That is a common error that you'll see in your SATs, ACTs, AccuPlacer, and of course in this class. Chapter 2, Section 4, Question 3. These are mixture problems. When I first was hired at this school, I was told, you need to be able to teach mixture problems. And I said, oh, no one can teach mixture problems. Teachers do a bad job of teaching it, students do a bad job of learning it, they get it wrong, and then we all move on with our lives. They said, that's very honest, but you need to learn how to teach mixture problems. So, I did a lot of mixture problems, And I can now teach mixture problems because we have a chart. Haha. Notice that this chart is much bigger. It's actually going to be 3 by 3. And what's going to happen is we're going to have the pounds of almonds. We're going to have the rate in the middle. Last time we had miles per hour. This is dollars per pound, which you'll see in pretty much any store. And then here is the dollars. So the dollars goes this way and the pounds go that way. A nut shop sells almonds and walnuts. We're going to take some almonds, we're going to take some walnuts. And almonds cost $10 per pound. Almonds cost $10 per pound. Walnuts cost $20 per pound. This is a very expensive shop. The shop has 21 pounds of almonds. 21 pounds of almonds. A mixture of almonds and walnuts. So we're going to have a mixture here because it's a mixture problem. A mixture of almonds and walnuts will cost $17 per pound. A couple things to notice here. First of all, you need to have 4 pieces of information. 1, 2, 3, 4. If you have more or less, you've done something wrong. Also, if you put cheap almonds, which are $10 a pound, with expensive walnuts, which are $20 a pound, the mixture should cost somewhere in the middle. So that is a quick check to make sure that you've put your numbers in the right spots. Now, those 4 pieces of information are enough that we'll be able to fill in the rest of this chart. The question says, how many pounds of walnuts did the shop use? We're going to use our favorite variable of x for the number of pounds of walnuts. X is the number of pounds of walnuts. Let's say that this was 5 pounds of walnuts. If you put 21 pounds of walnuts with 5 pounds of walnuts and mix them together, you would then have 26 pounds of walnuts. The way you got that is you took these and you added those two to equal that. 21 plus x equals, now I could put 21 plus x, but I do want to keep in mind descending order by degree, so x plus 21. Notice that it doesn't work here. 10 plus 20 is not 17, but remember that if you mix cheap stuff with expensive stuff, the mixture should be somewhere in the middle. Now, if I have 21 pounds and it's $10 a pound, each pound will be $10, $10, $10, $10, $10, $10, which means that as we go across, we're actually going to multiply to equal that. So 21 pounds at $10 a pound, $210 in almonds. They're a shop, they can do this. X times 20 gives us 20x. And a binomial times a monomial, I want my 17 times x plus 21. Monomial first, binomial second. Just like this was first box plus second box equals third box, same pattern will happen here. That is our equation. 210 plus 20x equals that. 210 plus 20x equals 17 times x plus 21. Now, variable equation. That right there is half credit on this problem. That's wonderful. But we need to solve it because we don't want half credit, we want full credit. We're going to use the distributive property. I know that we could multiply that out, but for speed of lecture, 17 times 21, we have 357. We are going to be moving the x's to one side. I'm moving my smaller x. And if you can handle this, we are going to move the numbers in the same step. 3x equals 357 minus 210 is 147. Dividing on both sides by 3, and we get x equals 49. We have 49, and then that means we're going to have 49 pounds of walnuts. Chapter 2, Section 4, Question 4. It's another mixture problem. This time I'm going to give you slightly different information and have you solve it anyway. So I've already drawn a mixture problem chart. This time, a coffee shop is selling espresso and Kona coffee. Espresso costs $7 per pound. Kona coffee costs $11 per pound. And the shop makes 12 pounds of coffee. It doesn't say whether or not this is espresso coffee or Kona coffee. is a mixture. So our mixture is here. So we have 12 pounds of mixed up coffee. A mixture of espresso and Kona is going to cost $8 a pound. How many pounds of each type did the shop use? Well, I can use X for one of them, but what do I use for the other? I am briefly going to put a happy face here. X plus happy face equals 12. If I were to solve for happy face, I would get that that is 12 minus X. Now let's see if this makes sense. If you had 12 pounds of coffee and X of it was espresso, then 12 minus X, meaning the rest of it, would be your Kona coffee. Another student pointed out that this makes a really cool pattern, kind of like a lightning bolt. And it goes from here, there, and it actually makes a little minus sign here as you make a little lightning bolt like that. X and 12 minus X. The pounds of espresso is X, and we're using 12 minus X for our Kona coffee. Remember that as you go down, you're going to add. If you were adding, the X and the minus X would cancel, giving you 12 equals 12, which is an identity from earlier on in chapter 2. As we go across, we're going to multiply to equal this. X times 7 gives you 7X. 11 times our binomial, 12 minus X, and 12 times 8. Double checking for the sake of our fast lecture. And again, over here, adding to equal that. You do not have to show this work if this makes sense. If this helps you, please use that. So our equation is 7x plus 11 times 12 minus x equals 96. We're going to use the distributive property, 7x plus 132 minus 11x equals 96, combining like terms. Oh no, when I combine like terms, 7 minus 11, that comes out as a negative number. It's okay. Negative 4x plus 132 equals 96. Because what's going to happen is when I subtract 132, oh no, I'm going to get another negative number. Negative 4x equals 96 minus 132 is negative 36. And when I divide a negative by another negative, it will come out as a positive 9. But wait, remember that if I have two defined variables, I need to find both answers. I have x and 12 minus x. I have to have x and 12 minus x. 12 minus 9 is 3. There's our handy dandy answer block that says if I have two variables, I have to solve for both of them. Notice that I kept the order the same as this. So we have 9 and 12. Nope, 9 and 3. But you have to label them. These are how many pounds? 9 pounds and 3 pounds. Chapter 2, Section 4, Question 5. We're going to do a mixture problem with money. Now, we're going to go back to using simple interest because that compound interest is a lot harder. So we're going to leave that for other classes. We're going to have our handy-dandy mixture chart. This time, the rate thing here, is going to be percent. And we're going to have our money going in and our money coming out. Now, this is the A equals P times R times T. We don't have a T column because technically if we did have a T column, all of this is going to be at the end of the year. The reason I'm pointing this out is that some of the college classes have had this over 2 years, in which case you'd have to change that. But these are all over 1 year, so that's why we don't usually have that column here. If it was over 2 years, then those would be 2s. So here, a person invests $15,000 in 2 stock funds. It would be too easy of a problem to say they put $15,000 in the first one and $15,000 in the second one. Instead, it doesn't tell you where the $15,000 is. That is a mixed up $15,000 that they have invested. Then, one fund earns 10% interest. 10%, the percents go here, but remember, we're not supposed to use percents in our equations. We have to change it into a decimal. And the other one earns 11%, which we have to change that into a decimal. You don't have to write the percents there. I'm just doing that to make sure that we can make the transition. At the end of the year, the person earns $1,600 in total interest. Not $1,600 from investment one, not $1,600 from investment two. It is $1,600 of mixed up money. Now this is an interesting problem because here, normally you take this times this to equal that. This box is blank and we don't actually use it at all because this is where our equation is going to be. We can call this x. We had this in the last problem, but just to review, I'm going to put a happy face here. X plus what equals 15,000. And so I'm going to subtract x on both sides, and I'll get that that is 15,000 minus x. So this is 15,000 minus x. Consider, if you had $15,000 and some of it went here, the rest of it would be there. You do not have to write this, but if it helps you, please do that. As you go down, you would add to equal that. If you were to add those, the x's would cancel and 15,000 equals 15,000. That is wonderful. As you go across, you multiply to equal that. So we get 0.1x, even multiplying by the 1. The multiplicative identity from chapter 1 says that timesing by 1 does not change anything. We want our monomial in front of our binomial. I'm running out of room, so I'm going to break down this wall here and keep going. And here is our equation. This plus this equals that. We could try and get rid of the decimals by multiplying by 100. But we have calculators and we can do this. I'm going to try doing this with a calculator and leaving the decimals in there. If you want to get rid of the decimals, we showed you how to do that earlier. 0.11 times 15,000. Aha, copying error. Thinking ahead. Combining like terms, it might be worth it to make this into a 2 decimals and 2 decimals, and we're going to get that. Oh no, it's negative. That means that we had better get a negative on the right-hand side, and when we subtract the 1650 over, we will get a negative. So there's a negative on the left. Be very careful when you're subtracting those to make sure you get the right number of decimal places. Dividing on both sides. We have $5,000 invested here. But wait, there were 2 variables there. Oh no, we have to define our variables. Otherwise we won't get our half credit. All right, there are 2 variables. Our equation, we're solving. We have to solve for both of those. So make sure you have that. Hey, that works out nicely. 15,000 minus x, x is 5,000. So this is the other 10,000. Now, these came out very nicely. Yours don't have to. It could come out as 5,500, 5,250, 5,750, something like that. But if it starts coming out with little decimals and pennies and things that you'd have to round, you've made a mistake. At this level of math, our answers are going to come out with relative, beautiful answers. it is polite to do 1, 2, 3, comma, 1, 2, 3, comma, to make them look like money.